Let's talk about chapter 9, that is 3D printing and design. 3D printing is also known as additive manufacturing. It creates objects by layering materials based on their digital model. So you have to prepare a digital model, and as per the model, printing will be done. Unlike traditional method, it adds materials where needed, reducing waste. It enables complex and custom designs that are difficult to achieve with conventional manufacturing. For example, if you have to manage a toy, you have to create a toy house. So you can do that with 3D printing. Right, so layer by layer, horizontally, the house would be built. Applications span across aerospace, automotive, healthcare, consumer good industries. 3D printing has the potential to revolutionize manufacturing from prototyping to end user parts production. In fact, it is already being used to create different parts. So, how does additive manufacturing work? We first have to create a digital model using a software like digital CAD, that is computer aided designing. The user will proceed to export the design as the .stl file. So that digital model is saved in a .stl file, which is acceptable format for 3D printing. So STL is a three-dimensional model of an object that can be converted into instructions for the 3D printing software. Now the user uploads the design into a program specifically designed for 3D printing, and this program is called Slicer. So you first create a digital model, then create the output of the digital model is saved in the STL file. That STL file is then loaded into a software called Slicer. The part design is imported as STL file. The slicer software interprets STL file based on user specific component and print parameters and converts it into a series of machine instructions for the 3D printer. So what is the role of slicer? It converts the STL file, the model in the STL file, as instructions for the 3D printer to print. Now, 3D printers use heat to liquefy the filament. For example, you must all have used the glue gun. So what you do is you need some thick molten material, and that will join two components. Similarly, you can visualize that to understand how 3D printers work. It uses heat to liquefy the filament. For example, if you have to make something from plastic, so it will uh, put molten plastic above the other in form of layers, so that particular object is created, allowing it to be extruded in a narrow nozzle with great precision. Once each layer is finished, the material undergoes a process of drying. So when you create a layer, you dry it so that it gets hardened, enabling the subsequent layer to be printed. So once the first layer gets over, it is hardened, then you print the next layer over it. So these 3D printing materials are often available in the form of metal, powder, or plastic. We will see what all materials can be used. The choice of materials in additive manufacturing techniques is quite diverse and depends upon factors such as quality and project objectives. For example, size, time, cost, and temperature resistance. So different materials used for additive manufacturing include nylon. We all know that nylon is an excellent resistance to both physical impact and chemical exposure. Then we have PLA, which is a polymer for fast prototyping because it is cost effective. Then we have TPU, which is malleable as well as durable, and it resembles rubber and is resistant to impacts. ABS is cost effective polymer, so we are basically using polymers here that has lower weight and durability. Copper, here we have metals. Copper is used for electrical applications, which is superior for thermal and electrical conductivity. Then we also have an alloy of nickel and chromium for applications that need exceptional resistance to corrosion, high temperatures, and chemicals. We have stainless steel that is used in many industrial production processes. Now, certain printers have capability to produce, so usually a composite, a mixture of materials is also used with reinforcing fibers, resulting in enhanced strength, durability, stiffness, and heat resistance. For example, the carbon fiber the Kelver aramid fiber, and the fiberglass. While carbon fiber is highly suitable for applications requiring high strength, flame resistant, and they are used in aerospace, automotive, and transportation sectors. Kevlar aramid fiber is well suited for applications that require exceptional durability, resistance to shock, and resistance to impact. Fiberglass, which is cost effective and is more durable than ABS, it is HSHT, that is high strength and high temperature fiberglass, retains its characteristics at very high temperature, reaching up to 200 centigrade. Now, some key terminology that we often use in 3D printing is slicing. Slicing means, see, we've already seen what a slicer is. It's a software which uses the digital model to create instructions for the 3D printer. Correspondingly, slicing, what is it? The 3D model is divided into thin horizontal layers using the slicing software. This program produces a file that is compatible with the 3D printer, which includes precise instructions for constructing each individual layer. Now, fused deposition modeling (FDM) is a process that involves melting and extruding thermoplastic filaments. So, it includes melting the thermoplastic filaments, right? Because we need molten plastic. Then SLA is a process that uses a laser to solidify liquid resin. For example, when we have the liquid resin, if you want to solidify, you will use the SLA process. SLS uses a laser to fuse powder material. So here it was solidifying, here it is fusing the powdered material. Then DLP is a technology. DLP stands for digital light processing. So here, as the name suggests, you are using the digital light projector. So instead of laser, you are using digital light projector to solidify resin. Then we have electron beam melting that employs electron beam to liquefy metal powder. So you have a metal powder, you to liquidify to make in a molten state. To liquefy it, you will use EBM. Then prototyping. It basically 3D printing is used for quick prototyping, production, medical. For example, we are now making implants, artificial body parts, and surgical assistance tools. In aerospace, it is used for creating both lightweight and intricate substances. Automotive use parts are manufactured using 3D printing technique. Now, what are the benefits? So, increased in-house production capability. You're no longer dependent upon an external entity. Anybody can have a 3D printer and quickly uh, create those things so that you don't have to share your technology, your trade secrets with any third person to who would print it. You can do it in-house, thereby protecting your intellectual property, proprietary innovations, and trade secrets. Cost efficient, then because it can be produced very quickly within months or even weeks. Reduced lead times, design freedom and process flexibility. You have the full freedom of manufacturing. Since you have the freedom, then you can make it a flexible process as per your requirement. You can create accelerated speed to market. Once it is available on time, you can speedily market it. Complete supply chain control is now in your hands from manufacturing to sales, fostering a culture of innovation. Additive manufacturing or 3D printing is a technique that involves creation of three-dimensional things by adding material in successive layers. So this is the proper definition. In contrast to conventional production techniques, which often include the removal of material from a bigger workpiece. Now, below is a comprehensive analysis of additive manufacturing. You can use it for designing the model, pre-processing the model, material selection, printing, post-processing, and quality control. Basically, these are the steps, I would say. First, you have to design the digital model. Pre-process it means if there are any errors, remove it. You can take a feedback and first finalize your digital model. Then you convert it into STL file. STL file is then imported into the slicer software, which creates instructions for the 3D printer. You can select the material, whether you're going to use some alloy, some metal, or some plastic or some fiber. Select that material and then start printing. After printing, you have to do some post processing, cutting, whatever it is, to make it a perfect shape. Then we need to check its quality. Additive manufacturing processes are classified by technology like laser sintering or extrusion. Then the materials vary from plastics, metals, and ceramics. Suitable for prototyping, end-user parts, or complex design, and each technique offers varying level of detail, material properties, and production scale. So here in this slide, we have summarized what we have done so far. Now, VAT photopolymerization. It uses this is a process which uses liquid photopolymer. So the name, in fact, itself suggests it's using photopolymer in liquid state resin in a container. It is hardened by because it is photopolymer. It is hardened by ultraviolet radiation, and it employs motor control mirrors to precisely you want ultraviolet radiation to make those radiations focus. You can use motor control mirrors for solidification. So use liquid photopolymer and use ultraviolet rays for solidification. The build platform moves downward and a laser trace pattern to form one layer at a time. Layer thickness ranges from zero point 0.0, so thin, 0 to 5 to zero point 0.5 mm, and each layer is covered with ultraviolet radiation. Two main processes happen here. Since we are talking about light photopolymer, we have DLP and SLA. Now, next process is material jetting. In this process, the print head, you can see the figure here, the print head deposits droplets of material on a platform. So the droplets come from this onto a platform. The liquid photopolymer resin is heated to a temperature between 30 degrees and 60 degrees to achieve optimal viscosity for printing. Char deflection plates enhance control, placing micro droplets with precision. Now we have deflection plates to make the drops come with very high precision. The droplets solidify to form a layer which is repeated to build the process. So here the first layer, then see here the subsequent layers, and finally more layers are added and this object is finally made. So layer by layer the object is created. Automotive companies use material jetting to create production devices for assembly lines. Next, we have binder jetting. For example, on t-shirts, you've seen some raised graphics, right? So that for that you can use binder jetting. Binder jetting uses binding agent and powder-based material. So you can see here the steps by step. So it applies the binding agent onto a layer of powdered powder particles. So here the process is repeated layer by layer to create custom components, and two, the binder consolidates layer by adhering them together in a liquid form. After coating, the product is placed onto a platform for further processing. For example, here you see powder is deposited. Inkjet applies binder. So this is the inkjet printer which applies binder. Each layer is printed first. So this is the first layer. Then powder is recoated. Again, you spread the powder. So here on the base, there is the first layer. Then you are again spreading the powder. And again, the inkjet is used to create the second layer. You can see there are some holes. So it creates a structure. Then you get the entire process is then placed on another platform for further processing. Next, material extrusion. So we have already read that material extrusion uses an electric motor that moves the nozzle horizontally and the printing bed. So this is the nozzle which moves horizontally and the printing bed here moves vertically. Layers of molten material are formed sequentially. So we have the molten material which is processed sequentially. Layers are joined through chemical bonding agents or by temperature control. Material extrusion is commonly used in affordable domestic 3D printers. Polymer materials in spools are pulled through a heated nozzle and deposited as a continuous stream. So here we have the nozzle, it's a material spool. whatever material fiber you are using or whatever it is in the molten here the material comes and it is heated with the heater element, and here the object is created. This is the bed which moves vertically, and it's the build platform where the material is getting created, and here if there's any support material. Directed energy deposition or DED. It's a highly complex form of additive manufacturing. Use here it uses concentrated energy sources like plasma, electron, or laser beams, heat, and fuses coaxial raw materials, wire, or powder. The liquefied material is deposited onto a substrate using a nozzle. So, everywhere we have a nozzle which deposits the material, and it is commonly used for metals like stainless steel, aluminium, copper, or titanium. So, here we see we have a molten alloy puddle, so it's being created here. This is the wire feeder, and the here it's the EB gun and re-solidify the alloy. So here the alloy is solidified. So this object is being created. If you see, this is a platform on which this object is created. Advantages of 3D printing includes rapid prototyping, as we saw, improved accuracy, minimization of material waste, so it's also eco-friendly. Enhancing energy efficiency, another reason why it is eco-friendly. Decrease expenses for small-scale manufacturing batches. Now you can produce in-house only, so you don't have to rely on others and you don't have to pay them the commission. Flexibility in the supply chain, decreasing the amount of inventory required because you can anytime manufacture as and when required. So that is also called just-in-time manufacturing. Eco-friendly, distinctive patterns, different types of patterns can be created, and there's a flexibility in supply chain also because high energy efficiency enables local production of goods without the need for extensive transportation. So another reason why we call it flexible and eco-friendly. Eco-friendly. So here in this figure, we can see machining. This manufacturing technique is used for production of metal items. However, it is also often used for creation of small to medium quantities of, although it is used for metal items, but can also produce plastic products. It is announced for its ability to create forms with exceptional precision and accuracy. On the downside, this process results in wastage of material in the form of deleted chips. CNC, also called computer numerical control, machining is a conventional production technique where machine tools are controlled by pre-programmed computer software to govern their movement. So machine parts are managed by computer software. So basically, it's a traditional way. Now injection molding, as the name specifies, here we have a mold, we have molds, and in that molds we put the material to create. This conventional manufacturing technique involves the use of pre-designed molds where pieces are manufactured by injecting liquefied material into pre-existing molds. So here we see these are the molds, and in the molds we place the material. So from the nozzle we get the material and it is heated, and whatever it is, fibers or pellets, and then the driving unit is shown and the object is created. Now another technique, forming. This technique applies to the production of hollow bodied and thin walled components. So there are thin walls and this body inside this is hollow. It entails the process of pressing hot thermoplastic sheets into specialized dies. So this is made of thermoplastics and onto the specialized dies. Then joining. We've heard seeing soldering. So those techniques, again traditional techniques, this process involves the fusion of partially completed components. Therefore, it creates intricate structure by combining basic elements due to the need for physical labor. The joining operation is well suited for small to medium-sized manufacturing. Some examples of joining procedures include bolting, welding, and adhesive bonding. Then real life application we've seen aerospace industry, energy sector, healthcare and transportation. CAD or computer aided designing for additive manufacturing. This is actually the backbone. We have various CAD software for designing prototype and products. It helps in creating three-dimensional models with precise forms and dimensions. For example, SolidWorks is a widely used CAD software. It is essential for both additive and subtractive means the 3D printing and the normal traditional way in which we manufacture. It aids in assessing and verifying product designs before manufacture. So CAD software is used to create designs, and those designs can then be used to manufacture either in conventional ways or using 3D printing. So the model design model created by the CAD software is also used to assess and verify, to validate the test product, the design of the product. So any CAD software works with different file formats. For example, the most commonly used is .stl. Other formats include X3D, DXF, ACIS, then JT, VRML, Parasolid, IGES, and STEP. Data translation in 3D printing refers to converting 3D models from one format, because we're saying data translation. So converting a 3D model from one format to another for basically compatibility, quality, or broader accessibility. For example, why do we convert a Word document to PDF? Because we want some features like it should not be editable, right? So we make it a PDF. The formatting should retain, so we make it a convert a Word document to PDF. Similarly, we can convert the 3D model specified in one format to another format, and that is called data translation. We know that STL format is widely used, and as it is compatible with most 3D printers, but it lacks color and texture. So you have to make always compromises. So the problem with STL format is it lacks color and texture data. OBJ format is more extensive than STL, storing geometry, color, and texture. But still, STL is widely used. For example, transforming a comprehensive CAD model created in software such as SolidWorks, AutoCAD, or Rhino into STL or 3MF format for the purpose of 3D printing. But when you do data translation, there's always some challenges like loss of detail, file compatibility issues, complex geometry, manual adjustment. For example, potential loss of geometric details or resolution during format conversion. Not all software and 3D printers support every file format. For example, if you convert from STL to 3MF, but 3MF is not supported by your printer, so then there is an issue. Then handling and translating models with intricate geometries or fine details without introducing errors is difficult. For example, when we used to earlier convert a PDF into Word, sometimes there was some distortion, some errors that automatically used to come in. Similarly, when you convert one model into another, there are chances that during the process of translation, some geometries or fine details may be lost. Manual adjustment, sometimes manual intervention is required to fix translation errors or optimize models for printing. Now, data loss in additive manufacturing refers to loss or alteration of essential design during the 3D printing process, as we've seen. This leads to error, reduced quality, and functional issue in the final product. Data loss can occur during design translation, file conversion, slicing, non-uniform scaling of the model, errors using during file transfer, bugs or crashes in software. So data loss can happen during translation, file conversion, slicing, scaling the model when we, for example, if our 100, the picture is in 100%, uh, and we convert it into 200%, we scale, zoom in or zoom out. So you see that the image gets distorted. Same is the case when you convert 3D models. Then errors can also occur during file transfer. If I'm mailing it to you, there can be errors, can be creep in, then bugs or crashes in the software. For example, decreasing the resolution settings during conversion results in reduced number of triangles or polygons, and therefore it is which are used to represent the model, leading to, for example, if you're reducing the number of pixels, so what will happen? Your image quality will go down. Similarly, we usually store models in terms of polygons or triangles. So if you try to reduce the resolution, the model will become less accurate. Other example, many CAD and slicing tools offer automated repair functions to fix manifold edges, holes, or other mesh errors that may result in data loss. Now, STL format encodes the surface geometry of a 3D object using a set of triangles. As we've seen in the last slide, and STL format represents the 3D object using a set of triangles. It does not retain information about color, texture, or other characteristics. This also we have seen. STL, which is commonly used for 3D printing, we now know. The format displays the unprocessed, unorganized surface structure of a digital model. The number of triangle increases with the complexity of the 3D model. More the number of triangles, the higher the complex the model is. CAD formats can easily be converted into STL files, making them suitable. So any CAD file format can be converted into STL. There are three main rules that is used in STL file format. For example, first is the vertex rule. According to this rule, it is required that every triangle have two vertices in common with the surrounding triangle. So here, this was not being followed. So therefore, we connected these two uh, vertices. The orientation rule, which says that the first rule separates the normal vector, the 90 at the 90 degree, should be directed towards the outside side. There's another rule which says that no, that is called the right hand rule. It says that the vertices are enumerated in anti-clockwise. So we will say this is 1, this is 2, and this is 3, not the other way around. Special rules, all positive octant rule. So as the name suggests, this rule stipulates that the coordinates of the vertices of the triangle must all be positive. This implies that 3D items should stay inside all positive octants of the, so no negative values, all positive values would be retained. Then the next triangle sorting rule says that the triangles must be arranged in ascending order based on their z values. So every triangle has x value, y value, z value. They should be sorted in ascending order of their z value. So this was all about 3D printing.